So is everybody back? Or are we happy to start? Okay, so this is just going to be a short sort of lecture, but it's really just going to be an introduction to this R-matrix code that we're going to use for the rest of the morning session and this afternoon. That's called Azure, and it's a C++ version of Azure. So this session will just introduce the code and give you an idea of what you expect to see, and then we'll go into a tutorial session after about half an hour. And there's a tutorial on the website, so you can log into the Talent server and run the code and get an idea of how you can do R-matrix analysis with a kind of full-fat R-matrix code that in principle you could use to do lots and lots of different things if you wanted to. The things we'll do today in the tutorial are relatively simple, but the code is very powerful and it will allow you to do lots of different things. Then once you've had a go with the code at some point this afternoon, maybe about 2 o'clock or 2:30, we'll come back over here and I'll say some more things about R-matrix analysis, things about background poles and sensitivities to radius parameters, and some aspects of using the code once you've had a go with it and been able to play around and see what it's all about, basically. So this is just about Azure, really. So first, some credits. It was developed by various people centered around the GINA at the University of Notre Dame, which is where I got involved back in 2005 on the Fortran 77 version. And the sort of primary people involved are Dick Azuma from the University of Toronto and Ethan Ubersender, who was a graduate student at Notre Dame and is now a postdoc there, and James DeBoer, and various other people have been involved along the way in developing this Fortran version. And then more recently, it's been rewritten in C++, which allows you to do, well, essentially you can do exactly the same things that you did with the Fortran version, but it's got a nice graphical user interface incorporated. So R-matrix calculations can be quite complicated if you've got a complicated situation. So if you've got many channels to take care of, lots of different data sets with all their own individual peculiarities, there are lots of things to keep track of. So this C++ version has a very nice GUI that helps you control the calculations and repair all the input and plot the results and things like that. And there was an earlier GUI for the Fortran version. And this C++ version is still in development. It was primarily written by Ethan, Dick, and James Burr. And this is the version we'll use today. And you can get hold of a version, well, you can get hold of either version. So the Fortran version is available on the website for Azure. You need to register. And then if you want to access the C++ version, you can just send James an email and he'll be able to send you, he'll be able to set you up so you can get hold of the C++ version. So that's the history of it. So the C++ code is written entirely in C++. It uses various libraries, including the GNU scientific library for calculating Coulomb functions and doing integrations and various things. And it uses Minuit 2, so it's C++ version of Minuit for fitting and doing analysis of parameter errors and things like that. It's parallel. It's parallel, so it uses OpenMP. So on a single computer, you can use all the cores of the computer when you're doing the fitting, which makes things a lot faster. And that's one advantage of the C++ version. It uses OpenMP. When you're using it this afternoon, because we're all using it on the same Talent server, things might get a bit slow. So I think I should have limited you to 1 CPU per person, because when there's 20 of you running on, I don't know how many CPUs the Talent server has, but it's probably not 20. So things might get a bit slow, but in principle, if you're using it at desktop, it might be a lot faster. In principle, you can treat all capture and reaction channels and elastic scattering reactions simultaneously, which means that if you've got data in elastic, you've got data in a reaction channel, a particle reaction channel, alpha p, and you've got data on capture reactions, you can treat all these things at the same time. So all the parameters for all the resonances, you just have one set of parameters for each resonance, and that resonance is appearing in all the relevant reaction channels, which helps you in principle get better constraint on all those parameters and helps you produce a more reliable fit. And then once you've done fitting, you can make extrapolation, so you can define particular energies and angles that you want a calculation at, and given a set of parameters, it will go away and make a calculation. So you can make extrapolations to low energy regions or different angles if you're looking at elastic scattering or whatever you like. And as I say, it's got a graphical user interface built using Qt, and it uses this QWT library for plotting. So one of the handy things is that you can do your calculations on the basis of the data sets that you've got, and then you can very easily see the results of the calculations in a separate tab. So you can keep track of what's going on, and you can fit by eye much more easily. You don't have to click in different windows, and it makes things very simple. Well, it makes things more simple than they were in the past, at least. So when you first open the code, this GUI window pops up, and so I've added something in here already for carbon 12 alpha alpha. But there are a few things that you need to set up first. So this window will open, there'll be no channels here. So no particle pairs here. This window will set all the particle pairs, but there are a few things you need to do first. So the first thing to do is edit so if you go up to, there's no menu here because I was using Ubuntu, but at the top there is, which will either be along here or somewhere else, there is an options menu, and you can edit the directory. So you just need to enter an output directory and a directory for check files. So this is where the code will put the output to. So generally we use output and checks. And so when you're looking for output files, they'll be in those directories. Most of the time, if you just want to look at a particular calculation and see how the agreement with your calculations with data, you don't necessarily need to look at the output files, but they're there if you need them. And it will, if you want, write various files to this checks directory, which includes sort of details of all the channels that are relevant and various checks that you might need to perform if you're comparing to other people's codes. Another thing to do, there's also up here in the menu, there's this edit options dialog. So this sets various runtime options, and in general you probably won't need to edit most of these. If things are getting slow this afternoon because there's lots of people running on the same server, one thing you can do is check this box for use the GNU Scientific Library Coulomb functions. So there are two sets of Coulomb functions in the code. One was written by Ethan, and one uses these library functions from GSL. These are less accurate than the functions that Ethan wrote, and so the problem is there are different methods of solution depending on the energy with the Coulomb functions, and you get slight discontinuities in the GSL Coulomb functions where you change from one method to another. Okay, so that's something to be wary of, but they are a lot faster. So if we find things are getting slow, it might be good to use those, and then you might see these slight discontinuities in the calculation. So this checkbox for using Broom formalism, this means doing the full calculation in terms of observed type parameters. Okay, so the input by default is input into the code is in terms of observed type parameters that are then converted into reduced width amplitudes using that. If you remember yesterday, we talked about the Breit-Wigner formula and the R matrix written in terms of these observed type widths. And then those reduced width amplitudes, those on resonance reduced width amplitudes are converted to a set of reduced width amplitudes with a fixed boundary condition. If you check this box, it will do the calculations in terms of those on resonance reduced width amplitudes. It's a technical thing, you probably don't need to worry about it, but sometimes it's useful to use Broom formalism if you want to fix particular parameters, because it gives you a better handle on fixing some parameters. There are some other options here that you probably won't need to worry about. If you ever happen to be trying to check calculations against another set of calculations from somebody else using a different code, it might be useful to use this do not perform parameter transformations, which means you can directly input the formal R matrix energies and reduce width amplitudes. But that's mostly just used for checking. So the only two things you need to worry about really here are these two up here. This Broom formalism check will make things a bit slower, so it's maybe best to leave that off because in principle it doesn't make any difference to the results that you get.
What's the main difference between the GSL Broom function and Broom formalism?
No, so these two are entirely separate issues. So the Broom formalism is in terms of is another way of writing the collision matrix in terms of a slightly different definition of the parameter set, and that's a bit more computationally intensive to do than writing the R matrix parameters in terms of a set of poles with a fixed boundary condition. So I don't want to go into the details too much, but and that's a separate issue from the Coulomb functions issue. So the Coulomb functions just come up a lot in terms of penetrabilities and shift functions and that sort of thing. And there are different methods of solving, basically. And this GSL method is a lot faster, but it's less accurate in certain places. So when you do a calculation, you might see a slight discontinuity in the calculation. It's just where the Coulomb functions are changing from one method of solution to another. So I wouldn't worry about it too much, but these are the only options that you probably need to worry about. And then you can also edit the check files. So by default, none of the check files are output, but you can output various things like details of the compound nucleus, details of the boundary conditions and the data, and these parameters that come in. The L matrix, which was this shift minus the penetrability, some phases and penetrabilities. And these are all useful if you need particular values to compare to other calculations and check things are doing it right. And you can either output them to the file or to a screen, but file is usually the most useful. But again, you probably don't need to use any of these this afternoon. Just be aware that they're there if you need them. So the example that we're going to look at, well, one of the examples is going to be carbon alpha scattering on carbon-12. And we saw this yesterday. So this is the sort of threshold schematic for oxygen-16 compound nucleus. So if you go up an excitation once you hit 7.167 MeV, that's the alpha separation threshold for carbon-12. And so this number will come up in a second. So the first thing you need to do when setting up an R-matrix calculation is define the particle pairs. Okay, so we have in this case, we have a compound nucleus that's oxygen-16. And we can define different particle pairs. So we could define carbon-12 and alpha as a particle pair, or we could define nitrogen-15 and a proton as a particle pair. And in this case, to start with, we're just going to look at this one. But what you can do is, there are various tabs along the top here. This first one is particle pairs, and this will be the first one that opens when you run the program. And what you can do is, you see in the bottom left, there is a plus and minus. So if you click the plus button, or the minus button, you can add and remove the particle pairs that you see, that you would see in this list. So there's only one here, but you will see more. And if you click add, you get a window pop up, and it says what sort of particle pair is it, so whether it says particle-particle or particle-gamma. And then you can edit various details for the light particle and for the heavy particle, the masses. This magnetic moment, the masses and this G factor, which is the magnetic moment, you don't need to worry about that at all. You can just set this to 0. Because it won't be relevant for the calculations that you're doing. And then, so properties for the light particle and the heavy particle, and then at the bottom, various properties for that particle pair. So the excitation energy in the final, for this particle pair. So for instance, if you were doing alpha scattering to alpha inelastic scattering, so you have the ground state of carbon-12 and an alpha particle in the entrance channel, and in an exit channel you have an alpha particle and an excited state of carbon-12. You could put that excitation energy in here. And then there's a separation energy in the compound nucleus. So in this case, this is where the 7.16 MeV comes in. So the separation energy here is how far above that threshold is in the compound nucleus. So in this case, it's 7.16. In nitrogen-15, it would be up at 12 MeV. And then a channel radius. So you can put, so you should check, in principle, the sensitivity of your calculations to this channel radius, but something of the order of 5.5 or 1.5 times the cube roots of the masses, for instance. Of the order of 1.5, but in principle, it shouldn't be sensitive to what you choose for the channel radius. At least the cross-section you calculate shouldn't be sensitive to this channel radius. And then once you've done that, once you've added this, you click accept, and you get a particle pair coming up here, and you'll have a list of particle pairs as you get if you have a more complicated calculation and there are more channels involved. And so this radius should be something of the order of the cube roots of the two particles involved times about 1.5 femtometers. And as long as it's big enough that you're outside what you'd expect for the range of the nuclear interaction, you should be okay. But as I say, you should check the sensitivity, and this afternoon I'll say something about the sensitivity to that parameter in particular, not parameter, that radius in this alpha scattering. Okay, so what we then need to do is add levels to the compound nucleus. So we've defined our different particle pairs, and by doing that we've defined what the compound nucleus is, and somewhere in this compound nucleus there will be levels at particular excitations. And then all we need to do is tell Azure what the spin and parity of the particular level is, and it will go away and calculate what all the relevant channels are. Okay. So again, we saw this yesterday. For carbon 12 plus alpha, the channels should be pretty simple. So the spins of our alpha, carbon 12 and alpha are both 0, and their parities are both positive. So the channel spin, which is the coupling of these two, is always going to be 0. And the spins of our resonances are always going to be equal to the relative angular momentum between the carbon 12 and the alpha. And the parities will be equal to minus 1 to the L. So the channels are pretty simple. We will have, in this case, if we're just having one particle pair, which is carbon 12 plus alpha, we'll have one channel per resonance, and we'll have one width to fit per resonance. So it should be pretty simple. So what we do on the left, so I've blocked out lots of things because these are relevant for the tutorial. The idea is that there are a couple of resonances that you want to determine the spins and parities of, right? So without giving these away, I mean, you could look at them up on NDC very easily, but I'll trust you not to do that. So what you do, once you've defined your particle pairs, you go to the Levels and Channels tab, and you can add resonances to the compound nucleus, okay? So on the left here, we have a list of levels that are in the compound nucleus, and I put a few in already. There are some narrow resonances here that are relevant in the region of interest. And you'll notice there are a whole load of resonances here at higher energies. So our separation energy for carbon 12 and alpha in the compound system was 7 MeV, 7.1 MeV. So if we see a resonance in our spectrum, its energy is going to be above that somewhere. Okay, so of the order of 8, 9, 10 MeV. And you'll notice that I've put lots of resonances here, all up at 20 MeV. So in principle, we need background poles. Okay, so in general, we're only taking account a few narrow resonances in the region that we're interested in, but in principle, there are an infinite number of poles higher up in energy. And we should at least consider taking those into account by assuming that we can bunch them all up into one background pole for each spin parity. So in principle, these resonances are there so that we can use them as background resonances. And whether or not we need them in each spin parity depends on the situation. So very often, certainly for reactions, you don't need strong background poles. Often for elastic scattering, you might need stronger background poles in more spin parity channels because the hard sphere phase shift doesn't necessarily do a good job of getting the sorts of non-compound nuclear scattering quite right. So these are there for two reasons. So firstly, we can use them for background poles, but secondly, when we're looking at scattering, you've got to make sure the hard sphere phase shifts are included. So in Azure, at least, these only get included. This hard sphere scattering only gets included if you explicitly include spin parities of each relevant, include a state of each relevant spin parity, right? So whenever you're setting up a calculation, the first thing to do is put in high energy states for all the possible spin parities, right? And that makes sure all these hard sphere phase contributions are included. And later on, when you're starting to consider the contributions from background resonances, you can use them as a background resonance by just giving them a width. And then fitting, right? And so there are various checkboxes here. So this first column of checkboxes says whether the state is going to be included in the calculation. So this gives you a very easy way to turn on and off resonances just to see their effect. If you want to see, you've got your calculation, you want to see the effect of removing that resonance, you can just click off this checkbox and rerun the calculation, and it gives you a very easy way to put things in and out. And this column, which says fix, means that if this is checked, the energy of that resonance will be fixed during fitting. So when you do a Minuit fit, it will only vary parameters that are not fixed. So in this case, it would vary the energies of these two resonances here. And you'll see on the right, so there's a second column which includes all the channels for each given level. And there's another fixed checkbox here for each of the channels, and this will fix the partial width for each channel. So if I click on a particular level, I'll get a list of all the possible channels for that level on the right-hand side. Okay, so in the middle here. So in this case, there's just one channel, and I've blacked out this S and L, so you can't work out what the channel is again. But there is a summary of all the information for that channel down here. So the light particle, the heavy particle, and their relative angular momentum and total spin are in here as well. And you can change how many channels are allowed by adjusting these things here. So you can change the maximum orbital angular momentum, and that's here set to 4. In general, for reactions that are relevant to astrophysics, you'll only need 0, 1, and 2 maybe, but in this case we do need 4. So for each resonance, as you click on it, you'll have a list of all the available channels here, and down here on the bottom right, when you click on a particular channel, you can edit the width, the partial width for that particular channel. So this is where you can set your width parameters before you do the calculation for all the available channels, for all available resonances. Okay, so yeah, and to add levels to the compound nucleus, you just click down here. A box will pop up, and you'll have something asking for the level spin and for the excitation energy, and then you can set the parity with this drop down. And then you get a list of levels on the left-hand side, and for each channel, for each level, you'll get a set of channels here, and then a summary of the channel information here. And down at the bottom right, you can set the width for a particular channel, and up at the top right, you can edit the allowed channels for all the resonances. And if you change these, all the allowed resonances, all the allowed channels will calculate automatically for all the resonances that are there. And similarly, you can edit a resonance by just double clicking on it. So if you double click, this box will pop up again, and you can shift its energy, and you can shift its or change its spin and parity if you really want to. But if you do that, be warned that if you change the spin and parity, obviously all the channels change. So because the different channel spins and orbital angular momentum will populate different resonances, right? So changing the level spin or the parity will change the channels, and that means you might lose information about the widths that were already in for that channel. But don't worry about that too much, because you probably won't need to do that. Okay, so in terms of the parameters that we have for the calculation for each resonance for carbon-12 plus alpha, because it's relatively simple, there's only one channel per resonance, you'll have you'll just have a resonance energy and a single width that depends on the channel orbital angular momentum. And for each spin parity, in principle, we also have a background pole. So with these background resonances, it's usually a good idea to fix their energy, because in principle it should be arbitrary, but you might, at some point you might want to check it. You should fix their energy to be something like 5 or 10 MeV above the highest energy data that you've got, so they're kind of well out of the scene, and you know that the tail of that resonance is going to be essentially constant as it goes through the energy region of interest. And then in principle they have width parameters that should be fitted also. Although usually, so as a general approach, it's usually best to identify sort of narrow resonances in the spectrum in the energy region that you're interested in and try and fit those, or at least by eye, estimate their widths and energies. And then later on you can add background resonances to improve the precise fit. So at least initially don't worry about giving these widths, just leave them equal to 0, and they won't be fitted in any fit. And then for each channel there is an R matrix radius, and in principle the cross sections that you calculate shouldn't be dependent on this R matrix radius, but you should check the sensitivity. And if there is some sensitivity, it might indicate that something is missing from the calculation. So the other thing is data and extrapolation segments. So segments are a way of handling different data sets. So particularly in many examples, there may be many sets of data that you want to fit. And this just gives you a mechanism for handling them, basically. So we describe each data set with what we call a data segment. And they look like this. So we have a list of the data segments in the top half here. So this shows you the reaction that the segment is relevant to. And then you have to set the energy range that data covers and the angle that the data covers, and whether it's differential, angular, or integrated. And then there's a file. And then in principle, you can have a normalization parameter for each data set. So what you can do is just click here, add, to add a data segment. And then you specify everything in here. So these two specify the entrance and exit channel particle pairs. So in this case, they're both 1, because which that referred to on our particle pairs tab to the carbon-12 plus alpha particle. And then you have some data file that contains the data. And all the examples this afternoon, they're a prepared data file, so they're all in the right format that you need. But if you want to do your own example and do something else, I can explain what you need in terms of a data format. It's not complicated. But you need to make sure that it's in the laboratory system for light particle on heavy particle. Okay, and that's just the way that the code expects the data. So for this data set, you then specify the energy ranges that you want to cover and the angular ranges. And the neat thing is that, so you notice all these segments have the same data file. Okay, so all of the data from this paper is in a single data file, but you have 5 different segments that pick out different subsets of that data. Okay, so this first segment just has all the data at 30 degrees, and then this second segment will have all the data at 45 degrees, and so on. Okay, so this gives you a useful way to handle data and organize data, and it's very useful when there are lots of different sets, right? So there's only 5 sets here, but these 5 data segments are all coming from one publication, one set of data. Now, in principle, all these data segments are sort of organized in a yield curve type fashion. Okay, so what you have is a single angle and an entire range of energies. So this is basically what we've been seeing when we've been looking at cross-sections. You see cross-section as a function of energy for a fixed angle, or angle integrated maybe. But the data segments allow you to look at angular distributions too, right? So instead of having a fixed angle and an energy range here, what we could do is put in a fixed energy for a particular set of data points in a range of angles. So if we could organize our data set to look at angular distributions rather than yield curves, which is quite useful if you're looking at scattering data and you want to try and tease out the spins and parities or resonances. And in principle, you know, there could be redundancy here, right? So if you want the same data set and you want segments for all the different yield curves, that's fine, but you could also add segments for angular distributions at particular energies if you want to. And that's fine. When you're doing a calculation, at least, it's fine because you can use these segments to look at the yield curves and you can use the other segments to look at angular distributions. The key thing is, well, the important thing is when you do a fit is to make sure that every data point is only included once. So if you have redundancy in your data segments, you don't want to be fitting the same data point twice because it will effectively reduce its error bar. But this gives you a very flexible way of organizing the data for different data sets and even the same data set so you can look at it very easily when we come to the plotting. So that's this sort of data segment. You can also define an extrapolation segment, so a segment without data effectively, but something that calculates for a particular entrance and exit channel particle pair over a range of energies with a particular energy step and a range of angles, or with whatever angle step you like, calculates cross-section. So this doesn't have data, but it says that I will calculate all the energies between 1 and 4 MeV in steps of 0.01. And this is what you can this is what you can use for extrapolation. So once you've done your calculation and you've put your fit parameters in the levels and channels tab, you can then define an extrapolation segment to calculate the cross-section at astrophysical energies, or whatever you want to use it for. And that's set up in a very similar way. So, okay, so there are some things I've skipped here. So the experimental effects allows you to include the resolution of the data, say. So your target may not be, if you've got a relatively thick target, there may be broadening of your data through stopping in the target, or if there is, your beam energy distribution is non-monoenergetic, there may be broadening effects that need to be factored into a particular data set. And these target effects can be used on a per segment basis. So if you have different data sets from different sources and they have different target effects, you should be able to take that into account. Okay, so you can define experimental effects for individual data sets and fit all of them simultaneously. But I'm not going to worry about that today too much. If you go to the right-hand end, you get the plotting tab, and you see on the top left we have the set of data segments that we saw on the segments tab. So there are 5 of them here, and these correspond to the different angles, and they've got a number 1 to 5 that corresponds to this number 1 to 5 over here. And similarly, at the bottom is our extrapolation tab here, segment here, and you have an extrapolation segment down here. And you can click on any of these you like, or as many as you like, and click draw, and it will plot all the data and the calculation that's in that segment. Okay, so here we have our data as a function of energy for a fixed angle. And so there are various configuration options up here. So we've got data segments, extrapolation segments, and the plotting options. So here you can plot either as the center of mass energy or as the excitation energy in the compound nucleus. And that's pretty useful if you're, so instead of plotting this, you'll plot this plus the separation energy for that alpha particle, right? And that's useful for identifying, because it means particular states, because you can very quickly identify what the excitation in the compound is, and then you can go and look up what energies, what levels are known to be in that region, for example. And it's also useful when you're looking at looking at channels with different entrance particle pairs. Okay, so with a center of mass energy, if you plot, if you happen to have if you have data sets, so for instance here we've got alpha alpha. Suppose we had higher energy alpha alpha data, and we were also looking at nitrogen 15p alpha. Okay, so those states will populate the same resonances, and in principle that alpha alpha scattering data can help constrain the widths for the p alpha channel. But if you look at the center of mass energy, the resonances will not appear in the same place in those two channels, because there is a difference in the separation thresholds. So you can plot this instead of center of mass energy, you can plot this in terms of excitation energy, and all the resonances in all the different channels will line up in the same place, so you'll be able to more easily see the effects. You can also plot this as center of mass angle, so if you're looking at angular distributions, you can change that there as well. And there are various options, so you can plot as cross-section or S-factor and logarithmic scales on both the x and y axes. So that's it, more or less. I'm just going to point out some nuclear data resources. So there are lots of different places you can get nuclear data from. You probably know NNDC, but Tunnel is very useful if you're looking at reactions with light nuclei, which many astrophysical reactions are. So they've got lots of information on masses less than 20, and they've got information on energies and widths, and they're often reaction specific. These are all hyperlinked in the PDF, so you should be able to get them. There's the Berkeley Table of Atomic Masses if you're looking for separation energies, and the Atomic Mass Data Center, and a chart of the nuclides. That might be my one, I'm not sure. Okay, and then there are various resources where you can get reaction data from. So X4 you've probably all used last week, but there's also IBandle, which is sort of organized by the, it's an IAEA database, but it's organized for ion beam analysis community. So there's lots of scattering data on here that you might not find in X4, and you might not come across looking in other ways, because often it's published in NIMB and it doesn't make it into the nuclear science databases. And there's also NACRA, which has lots of reaction, lots of S-factors and reaction rates available, and a link to the Azure website if you want to get hold of the codes. So the tutorial session that will start very shortly. So the main thing is to do an analysis of alpha scattering on carbon-12. It's a relatively simple example, but it should get you used to how you set up the code and how you do various things if you want to then do a more complicated example afterwards. So the idea is that there are two resonances in the data set that I'll give you, and you need to identify their spins and parities, and then fit the parameters of those resonances to optimize the fit to the data and establish precisely what the parameters are. And then there's an example, there's data for nitrogen 15p alpha, which I showed a lot yesterday, and then the sort of objective is to establish what an astrophysical S factor would be at something like 30 keV. So you need to identify the resonances and their spins and parities and fit their widths, and then make an extrapolation, right? So these are just some example things you can do, and then there's another example, sodium 21 pp, which I also showed yesterday, but you've got that data there to fit. So there are plenty of things to do, and you'll get all these data files, all the relevant data files for these when you start the tutorial. If you've got other things that you want to do, like I know some people are interested in doing R matrix analysis for projects, then feel free to ask me about them and start doing them. I mean, it's useful to go through carbon-12 alpha alpha first, because it will sort of familiarize you with it. But once you've done that, feel free to do anything you like, and I can help out. If things go wrong, so I've run this tutorial session before, and quite often, well, not quite often, but occasionally there were crashes, which often are related to external libraries. But they often occur in very particular circumstances. So if you get a crash, tell me straight away, and I'll try and get a copy of all your files so I can try and reproduce the crash, because last time it was actually quite difficult to reproduce the problems people were having after the event. Okay, so that's about it. So the tutorial is on the Talent website. If you just connect to the Talent server and then copy the files across using something like this, You'll have the directory and subdirectories with each example and the data files. But you need to do this once, and then you should be good to go. So that's it. So this afternoon, once you've had a go at using, or at least started on the Carbon 12 Alpha Alpha example, we'll come back again this afternoon, and I'll say some more things about background poles and sensitivities and things like that. But that's about it. So go for it, and we'll see how it goes. Okay. About an hour. Okay. Yeah. Just see how it goes.
The socks is